come along and talk on this topic. It's a really interesting topic. This one I'm going to talk about actually has the potential to really revolutionise sugarcane variety improvement. So it's a good opportunity to sort of share some of the information here. There's two parts. I'm giving a bit of a talk on the background to this work, why it started, why it's important. And then I'm going to hand over to Terry who will talk about the operational aspects of the Wilmar program. So just by way of background, I've been in the sugarcane breeding business since 1988. So I started at Macnade at 31st of October 1988, and I worked in the Herbert, so I know some people here. I worked in the Herbert for 7 years, and then I went and worked more on the verdict and worked running the BSS and CSR breeding program down in the verdict, and up until the end of when BSS stopped in 2013, whenever it was. And then all along that time I've been involved in a lot of research to try and improve the process of sugarcane variety improvement. And I can only say that, boy, I really wish I knew what I'm going to talk to you guys about today. I really wish I knew back when I started sugarcane breeding, because boy, it would have made a huge difference. And you'll see why when I talk about this. So, two parts of my talk. Firstly, I'm going to talk about the current problem with sugarcane breeding, and there is a big problem. I think everyone here is aware that sugarcane improvement has not been going forward very fast, and I'm going to talk about that. And secondly, then I'm going to talk about genomic prediction, and that's one way that we think can help this situation. So, sugarcane yields aren't increasing as much as other crops, including sugar beet. It's the main worldwide competitor for sugarcane, and it's a big concern. So just some data. If you look at the major crops and you look at the number of crops, these are the biggest 4 crops on a worldwide basis. The yield as a percentage of what it was in 1961, so everything starts at 100% in 1961. And going forward to nearly these are slides that I actually presented at an International Society of Sugarcane conference in 2019. That was a little bit, only a couple of years old, but basically there's been a 2 or 3-fold increase in yields in all the major crops since 1961. So if you had yields basically increased in all those crops by 2 times or 3 times. And there's been a lot of studies published on why those increases have come about. Most crops have increased yields between 2-fold and 3-fold. Usually 50 to 80% of the yield increase is attributed to breeding. That's conventional breeding, that's traditional selective breeding, not GM or anything, just traditional breeding. And they're keeping on going up. They're linear increases. There's no sign of plateauing at all. And that's I've just got 4 examples here, but that's the same as with most major crops. That's the rate of increase. Sugar beet is also going up a lot. Sugar beet's doubled in the last 30 years or so. They're really doing well, and actually it's a real worry actually for sugarcane, because the farm gate cost of production of sugar from beet, as a paper out a couple of years ago, is now on par with sugarcane. And 30 years ago we just never would have believed beet would have competed with sugarcane on a cost basis, but the yield increases are so great that beet is now, at a farm gate level, is now competing with cane. So that has to be a big worry for cane producers worldwide, because beet's going up like crazy.
Is that taking into account, Phil, that the processed beet they got supplied by energy or supply energy milling?
Sugarcane's still ahead at the processing level, because they've got the higher level of fibre and they can use that for energy production. But that I'm talking about at farm gate level now, the cost of sugar production from beet is very similar. As a paper comparing from in Europe with Brazil, and they're pretty much the same at farm gate level. But I guess the worry is beet's going up like that, as you can see, and the cost of production of beet is still going to keep coming down. Cane isn't doing that. So looking at the cane, so about over 50% of that gain is attributed to breeding new varieties of beet. So their breeding programs are working really well. This is the bottom line there, sugarcane on a worldwide basis. So cane's gone up maybe about 60%. Australia, I haven't got the Australian data here, Australia's a bit less than that. And over the last 20 years, it's gone basically nowhere. So there's a big problem. So the key just to summarise that data, last 50 years, major crops, a whole heap of major crops have gone up by greater than 200%. Beets doubled in the last 30 years, and sugarcane is much smaller improvement. In fact, as I say, in the last 20 years or so, it hasn't gone very far at all. So the first question is why? And I'm going to explain to you why we've got this problem. So most people here are probably aware of the overall process associated with sugarcane breeding. I'll just go through this quickly because I want to emphasise some key points, where the problem is. So we start at crossing, we go through a multi-stage selection process. That people here will be familiar with. The seedlings get planted and they get whittled down in numbers over a period of 8 to 10 years or so, and you get the advanced stage trials, and then any variety that's good enough gets released to the industry. So the process starts with selecting parents. Typically these are the clones that have performed well in trials initially. They put in crosses, and in Australia we've got the small McNade facility, and most of the crosses are made up of Moringa in the SRO program. So they're crossed together. Then so the crossing happens there, seedlings get planted out, seedlings planted in the field here, and each year in Australia about 100,000 seedlings get planted out. And you can look at the performance of the seedlings on a sort of bell-shaped curve here. So this is a population of seedlings, and some of the really good ones are on the right-hand side, they've got very high yield, and some are very low yield. Most of them are in the middle. Most of the big numbers, this is the number of clones. And most is a typical bell curve that you get with any sort of trait in a population. You get a very small number of good ones, a small number of really bad ones, and most of them in the middle. And obviously what we're interested in are the ones that are on the right-hand side of that curve, the really good ones. And as I said, you can look at consider that as a bell curve there. And then finally, advanced stage trials, which everyone's aware of. These are at the later stage, accurate data on a small number of clones that have made it through that multi-stage selection system. And anything that's good enough gets released for growers to try out on their farms. And then very importantly, good clones at the end. Typically maybe in the herbert here, say 50 or 60 clones that have done really well at the end get cycled back to be used as parents for an ongoing cycle like that. And so what we hope with each cycle, we hope that this curve of seedlings jumps forward. So this curve here, next cycle we get the best parents. If we're making progress in the breeding program, that curve jumps forward each generation cycle. Like that. So, most of us in the past, including myself, up until not 5 years or so before my retirement, we all thought this was the most important part, the seedlings to the release of cultivars. And that's what people in the herbert here see too. You see the trials, and you wonder whether they got the trials in the right location. You wonder the procedures are right and everything. In fact, I was involved in a review and the herbert program, I think it was 5 years ago, and why isn't the program here performing very well? The focus is on what happens here in the herbert, in the trials on the herbert. But in fact, if we look at that process, and this is the same not just in the herbert but in all regions and in fact most programs in the world, we look at that process, it is actually working fairly well okay, in that the best seedlings that come in here at the front have got a pretty good chance of being taken out, selected out the bottom end. This became apparent about, we did a big project in 2010. We developed an accurate model of that whole process, and we found that we could improve it a little bit. We could twiddle around with it, but it wasn't. What was happening was fairly optimal. So we were identifying the best material coming that was entering at the start. Where the problem is is in the parental selection path. So we're not going forward. With this seedling population, we're not moving forward. And that's because the parental selection is very, very ineffective. It's not jumping forward. So in fact, the problem with the program here is not what happens here in the herb. The problem is actually what happens at Moringa and the parental selection path. I'm going to talk about that in a little bit more detail. So what's happening is that this seedling population over time is not jumping forward. In fact, the population that we had back in, when Lawrence first started the BSS program, remember, you grew seedling back in 1990. If you looked at, Lawrence, if you looked at your seedling population back in 1990 and you looked at the seedling population they're growing today, it would be very similar in fact. And in fact, so this part is working, it's identifying the best clones coming in, but these aren't really jumping forward very much. That's where the big problem is. And every so often we find something better than has been found before, but it's like going to a casino. It's really rare and it's really by random chance, because we're selecting from basically the same population over a long period of time. So I guess it's like, what we've been looking at. We've been looking at this part of the program for a long time. Everyone's been looking at that hard, trying to improve it. But it's like you have a racing car, and the racing car's not performing, and you bring it in, and it's got 4 flat tyres, and you tune the engine. And you tune the engine, you send it back out. Okay, tuning the engine is important, but until you change the tyres, it's still not going to perform very well. So that's what this is like. We can tune this up as much as possible, but until we make this part jump forward, it's not going to go very far. And so there's a little bit of technical detail. The reason is because if we take a whole set of varieties and we correlate the yield of those varieties with their breeding value, which is the performance of that progeny, that's not correlated very well. It has a slight correlation, but it's not a very high correlation. And so that's basically what's happening. We're picking out the best varieties here in terms of the yield, but they're not necessarily the best parents. And you can think of, there's lots of examples. Think of Q124, which is a fantastic variety, but never was a very poor parent. And lots of examples like that. So we're not picking the best parents. There's 2 definitions here. There's breeding value of a variety, which is performance of its offspring, and that's affected by the effects of individual genes independently, and that's called, breeders call that additive genetic effects. Then there's the cultivar value of a variety, which is what growers are obviously interested in. This is the direct performance of the variety. That's affected by those individual genes, but also combinations of genes, complex combinations of genes. And that's called, those complex combinations are called non-additive effects. So those, when we're selecting parents, we're interested in the additive genetic effects. When we're selecting for cultivars, we're interested in the total of all the genetic effects. And because in sugarcane particularly, these non-additive genetic effects are very large, that means what is a good variety is not necessarily a good parent, and which is why our parent selection, this is the bottleneck problem. The problem is this cycle here. So the question is how to address this problem. As I said, the focus, it's still the focus of many sugarcane breeders. In fact, probably most sugarcane breeders still focus on that selection part, and there's very little focus on the parental improvement part, unfortunately. So how to address the problem? There's different ways that the problem can be addressed, and some of them are traditional breeding. And you think of corn and even sugar beet. They've got those special. They also have this problem to some extent, probably not as much as sugarcane, but they develop very complex breeding systems. And with corn and sugar beet, you've got F1 hybrids, and so they actually develop 2 parental pools, and they cross them together to deliver F1 hybrids. And these sort of schemes could be used in sugarcane. But sugarcane, I guess, it's just been people. I don't know whether it's complacency or what, but we've been using the same scheme for over 100 years. And there are other ways that we could address this problem. Now, the modern way, one of the ways that can be used is this, what I'm going to talk about next, which is genomic selection. And this could kind of circumvent a lot of those other complex ways and address this problem directly. So just a little bit of background. DNA markers. So genomic selection uses DNA markers. I think most people are probably aware that DNA is the code, exists within every cell in every living organism, and it's the code that creates enzymes, which creates how a plant or an animal will grow and yield and everything like that. And there's all these, it's made up of millions of these what they call bases, and that code, the actual combination of those bases, the order of those bases determines the genes, which then produce the enzymes, which produce the growth and so forth. And if we looked at the DNA of all of us in here, 99.9% of it would be similar, but there's a few little differences, and those little differences determine our different traits. And the same with sugarcane. Every variety, 99.9% the same, but there's those few little differences. And those little differences we can detect. And we can detect them with different technologies, but those different technologies will produce what we call DNA markers. And so we might have grow 1,000 varieties out, and 500 might have this marker, and 500 won't have that marker. And we can compare the 500 with the marker and those without the marker. I mean, if there's a yield difference, we can say that marker is linked to a gene that causes that yield difference. So that's what DNA markers are. Now, we've been working on DNA markers for a long time, since the 1990s with sugarcane. My organisation, CSIRO, and BSES and SRA, and many others have been working on DNA markers on sugarcane. And one of the early methods of using DNA markers was to run it out the gel, and each one of these is a different variety, and you can compare, say, these two varieties here. This variety here has got this marker, this one doesn't have that marker. And this early method of looking at DNA markers, but they were really, really labour intensive up until about 2010. And we showed that we could use DNA markers, but they were so labour intensive that it didn't really, it was just too difficult to apply them in the breeding program. But in the last 15 years or so, there's been very big developments in DNA technology, driven by heaps of work in humans and animals and other plants. And in 2015, a microarray technology was developed for sugarcane, which we could screen 58,000 DNA markers on sugarcane. And this has been used to predict cane yield and CCS in sugarcane, and it works quite well. So that opened up the opportunity to start using this marker technology in sugarcane. So, coming back a little bit of technical detail again, as I said, the breeding value of a variety, which is how good it is as a parent, is affected by the independent effects of many genes. It's called the additive effects. And DNA markers, we know, can accurately predict those additive genetic effects. We still can't predict the non-additive effects very well, because they're very complex and just too difficult. But these additive effects can be predicted quite well with DNA markers. And so using DNA markers for this purpose, to predict breeding value, obviously can address that key problem that we've had with sugarcane breeding, which is that lack of parental improvement. So genomic selection is already revolutionising breeding in animals and other plants. It's used, as I said, to predict parental breeding values. It's been used now widely in animal breeding. In dairy cattle, for instance, as soon as a bull is born, they get its breeding value, they retain the top 1% for breeding, and as soon as it's old enough, its sperm gets distributed for artificial insemination, and all the rest of them are culled. And so they have a 2-year breeding cycle, really rapid breeding cycle, and it's revolutionised dairy cattle improvement. Dairy cattle improvement's going like this because of genomic selection. Actually, the dairy cattle industry was the first industry that started using this technology at a commercial scale back in about 2003, 2004. We started testing this in sugarcane in 2009. This was done through the Sugar CRC, which was work was done jointly by CSIRO and SRA and Wilmar. Trials were done down at Colombia and Burlington. And we showed that it could work well, and it's written up in a final report in 2015 and a paper in 2016. So how it's used is that you start off with a training population. Actually, this slide's a bit different than one we'll get the next one. So you start off with a training population, evaluate several thousand genotypes of varieties and for yield and sugar content. Also screen them with the 58,000 markers, and from that you develop a prediction, a complex equation that can predict the yield and sugar content just from the DNA marker data. So you don't need, then thereafter, once you've got that prediction formula for any variety, you don't need to measure its yield or CCS and also disease resistance. You just have to screen it for these markers, and then you can predict what its breeding value is going to be. So this part has already been done by University of Queensland, SRA and CSRO. But once we got that array, that work has been done. And then it's a matter of applying it into the breeding program. Sorry. Applying it into the breeding program. And then, so that involves screening in an early stage in the breeding program, seedlings, and then predicting the breeding value, and then taking them straight back to be used as parents. So there's two advantages in this method. One is it provides good accuracy for predicting the breeding value, which we haven't got. As I said at the moment, we can't predict the breeding value very well because the performance of variety doesn't correlate very well with its breeding value. And secondly, instead of having an 8 to 10 year cycle, we've got a 2-year cycle. So we can circle around here very quickly, make rapid improvements. And this is the same sort of thing that they're using in dairy cattle and other crops. So really rapid, accurate breeding value predictions, whirling that round quickly, still run things through the trials to get out the best clones for commercial use, but you're improving breeding value and making those seedling populations go forward over time. So that's the overall technology. That's how it should work. And as I said, we have tried it at a pilot scale, and now it's being done at a more commercial scale tested it at a more commercial scale by Wilmar. There's a lot of, so just some other comments on this. There's a lot of DNA marker research funded, reports written, recommendations made, and unfortunately, like a lot of research in the sugar industry, a lot of it finishes up as reports and is not implemented. You know, and I was so frustrated after we did all this work in 2015. The breeding program, the breeding program doesn't take it up. And so, from my personal point of view, it's fantastic to see Wilmar take this up and actually run with it at a commercial scale, and not accept that the current rate of improvement which is pretty well zero, is okay. So, I'm just really pleased that Wilmar are giving this a really good shot. The technology is definitely having a big impact in other industries, and I predict if in sugarcane, if it's done well, it really will improve rates of variety improvement, not just in Australia but worldwide, because it is a worldwide problem with sugarcane. My only caveat is that it is new to sugarcane, and it will definitely need close monitoring and adjustments as time goes by to maximise the chances of success in this area. So that's all. Just introduction to the technology, and I'll just hand over to Terry now to talk, I guess, about